Have you ever wondered why there is such little effort required by the driver to press the brake pedal? The brake booster plays a major part when applying the brakes and stopping the vehicle. Because most vehicles are now fitted with disc brakes, vehicle manufacturers cannot utilise the self-energisation effect that four-wheel brake drum and shoe systems develop. So a different method of force multiplication is required for a vehicle using brake rotors and pads. Vacuum suspended brake boosters are the most common force multiplier used in automotive brake systems. And although there are many different types, they are all similar in operation. They provide braking assistance by applying a vacuum or low pressure to one side of a diaphragm and allow atmospheric pressure to push on the other. The force produced by the brake booster reduces the pedal effort required by the driver, while at the same time it increases the force applied to the master cylinder hydraulics. We call these components vacuum brake boosters, but be aware that the term vacuum is only used to indicate a negative or low pressure, which is any value below atmospheric. In the past, all gasoline-powered vehicles used manifold pressure to operate the brake booster. Although, due to modern engines using variable valve timing, most are fitted with a mechanical vacuum pump, just like a diesel. A brake booster operates in three conditions: apply, released, and hold. Released refers to when there is no driver application of the brake pedal. With the engine running, the air in the front chamber of the booster is exhausted to either the intake manifold or vacuum pump via a reinforced rubber hose and check valve. This chamber is pulled down below atmospheric pressure. The control valve, located in the rear chamber, has its vacuum port open. This allows the rear chamber's pressure to be pulled to the same level as the front. When both chambers have equal pressure, the diaphragm is held in the release position by the heavy return spring located in the front of the diaphragm. The control valve is attached to the brake pedal pushrod, and as such, it's operated by the driver. When the brake pedal is pressed, the pushrod acts on the control valve in the brake booster. This movement operates a poppet valve, which shuts the vacuum port and opens the atmospheric port. The atmospheric pressure entering the rear chamber imbalances the booster and moves the diaphragm forward, overcoming the return spring, forcing the front pushrod into the master cylinder. It's the atmospheric pressure acting on the diaphragm that assists the driver to apply the brakes. As long as there is forward movement of the brake pedal, the poppet valve allows atmospheric pressure into the rear chamber. When the vehicle comes to a standstill with the driver holding the brake pedal steady, the booster is in its holding or balance position. The pressure developed in the master cylinder acts against the booster's pushrod and reaction disc. The poppet valve is lifted from its seat, closing the atmospheric port. Because the vacuum and atmospheric ports are both closed in the hold position, this action retains a pressure in the rear chamber that balances both the diaphragm spring and front chamber negative pressure. The booster will remain in the hold position until the driver depresses or releases the brake pedal. An increase in pedal pressure will move the control valve poppet off its seat to admit more atmospheric pressure to the rear chamber and therefore apply more force to the master cylinder. When the pedal pressure is relieved, the plunger and poppet will move back to the released position. This will open a vacuum port, allowing the rear chamber to be evacuated. The diaphragm return spring will then move the diaphragm back to its release position. The amount of force applied to the master cylinder is dependent on the diameter and surface area of the diaphragm. The force is calculated using the pressure differential across the diaphragm, multiplied by its surface area. The pressure differential can be found by subtracting atmospheric pressure from the engine vacuum pressure. A 4-cylinder engine produces about 17 inches of mercury, or 45 kPa at idle. Since atmospheric pressure at sea level is 103 kPa, our pressure differential is 58 kilopascals. If the diameter of a given diaphragm is 12 inches or 305 millimeters, the surface area would be about 113 square inches or nearly 73,000 square millimeters. Therefore, the resulting additional force applied by the brake booster would be 870 pounds or 3,870 newtons. The brake booster and hydraulic circuits are individual systems and should always be checked for faults separately. We can perform a quick check of the brake booster's operation by exhausting the unit's chambers to atmosphere, then reducing its pressure once again. With the engine off, simply pump the brake pedal several times, or until it feels solid. Then, with the brake pedal pressed firmly down, restart the engine. We should feel the pedal fall slightly as the air pressure in the booster's front chamber is reduced. This test also checks the booster's internal and external valve operation. A hard pedal could be caused by collapsed or leaking vacuum lines, insufficient manifold vacuum, punctured or a leaking diaphragm, a blocked check valve, or a faulty control valve. A steady hissing sound when the brake pedal is pressed may indicate a vacuum leak within the brake booster assembly. Correct adjustment of the master cylinder pushrod is essential to ensure correct operation of the brake system. Insufficient clearance will cause the master cylinder piston to cover the vent port, resulting in brake drag. On the other hand, if the pushrod is too short, it may cause excessive brake pedal travel. Checking and adjusting the length of this pushrod is relatively simple, although special tools and clearance specifications may be required for different vehicle makes and models. The pedal pushrod assembly should also be checked for correct free play. Again, incorrect adjustments here may result in dragging brakes or excessive pedal travel. It's always important to check the manufacturer's specifications and procedures when performing any adjustments. A strong understanding of how a brake booster operates will ensure technicians can locate brake problems quickly and efficiently.